Hello everyone, I am Akash Kumar. I will present this work, Self-Supervised Learning for Multiple Object Tracking in 3D Point Cloud. This is a joint work with Jyoti Gini and Dr. Mubarak Shah from University of Central Florida and Dr. Ajmal Mia from University of Western Australia. Motivation of this work is as follows. Labeling video or LiDAR data is laborious task and also prone to errors. And expensive notation and lack of diversity in the samples have been some major challenges in the area of supervised tracking. And also the curation of training data, especially for supervised tracking, involves immense human efforts, especially to annotate those identity associations of objects in LiDAR data. So we exploit self-supervised based learning so that we can leverage from large unlabeled data pool to learn useful representation for performing 3D multi-object tracking. Our major contributions are as follows. We propose state-of-art SS3D MOT model for multiple object tracking in 3D point clouds. We propose self-supervised training techniques using real data as well as synthetic data. We show that the proposed model is agnostic to the shape of the object being tracked. So at training time, we use basic geometric shape to learn the identity association across the frame. In inference time, we are able to track pedestrian as well as cars. And we achieve state-of-art results. Our approach is as follows. Given a LiDAR frame, here we show the LiDAR frame from Jackrabbit dataset. We use ground truth 3D detections and crop the objects. Afterwards, we apply augmentation techniques and create two augmented frames. So each object is augmented in such a way that we apply translation, rotation, and cutout. So since these two augmented frames are coming from the single frame, we know the correct identity association across them. And then we limit the number of points per object and create this 3D tensor which represents all the objects within the frame. In parallel, we also perform same augmentation techniques on the corresponding bounding box of the objects, and then we use feature extractor to extract the features of bounding box as well as the objects. We concatenate them, perform exhaustive pairing permutation, and use the affinity predictor, which is a 5-layer convolution neural network, to extract the affinity matrix M of size n by n. We also append extra row and column to accommodate for the objects that are entering and leaving the scene. And we use two types of losses to train this model. One is the forward association loss, another one is the backward association loss. We also train our model using synthetic LiDAR frames. We create synthetic LiDAR frames as follows. Given the objects from ModelNet 40, we place those objects at different 3D locations, perform augmentations, and create two augmented frames to train the model. Similarly, we also use basic geometric shapes like cone and boxes to create a synthetic LiDAR frame and perform augmentation and create two augmented frame. When we train our model in this setup, we get really good numbers. So creating synthetic LiDAR frame, we not only eliminate the need for correct identity association, but we no longer need real data set as well as the ground truth detections to train our model. We apply following augmentation techniques to train our model. Number one is translation. So through translation, we introduce displacement in corresponding objects across the two augmented frames. We translate each object by 0.1, 0.2 or 0.4 meters randomly in either x, y or z direction. And then we apply rotation. Through rotation, we incorporate angular motion within the objects. We rotate either with 5 degree, 10 degree or 15 degree randomly. And then we introduce cutout. So through cutout, we simulate occlusions and we cut out small portion of the objects vertically. Here we show quantitative results of our method on two datasets. One is the Czech Report dataset, other one is the Kitty dataset. So these are the results on validation dataset. Here we show results using supervised as well as self-supervised data. In self-supervised setup, we train it in with three different settings. One with the real data, other one is with the synthetic data using CAD objects from ModelNet 40, and the third one is synthetic data where we use primitive shapes. So we can see that our results on supervised as well as self-supervised settings are very close. Here we show the ablation study of augmentation techniques. Using only translation, which introduce displacement across objects, we are able to get really good results. But when we add cutout and rotation to simulate occlusion and angular motion, our ID switch is reduced and MOTA increases. These are the qualitative results for kitty pedestrian. On the bottom part, we show the LiDAR view. On the top part, we show the image view. For training, we have used LiDAR part only, but to visualize, we are adding the images. These are the results on kitty cars. These are the qualitative results on JRDP dataset. These are the results on the test dataset of Jackrabbit data. Here we show the results on supervised as well as three self-supervised techniques. We achieve state-of-the-art results compared to other methods. And this is the screenshot from the Jackrabbit dataset leaderboard where our method SS3D MOT stands on the top. Thank you for listening me. If you have any question, feel free to ask.